video report. And just I wanted to say a few things for the ones who are new. If you need Wi-Fi access, you have to sign up here, and you get a account and a password. Here I can do it. Also, if your name badges are also here, if you come to me maybe in the break. The other thing is the most important thing here is we are here in this room, blue. Lunch will, this is wrong, lunch will be in the yellow room and also back there, but you will get it in the yellow room. And the toilets are just here. So if you go out throughout this door, and the next two doors on the left are the restrooms. And in case of emergency, then the access is here. You go out through, and on the other side of this wall, there's a door. So that's for these parts, and yeah, that's it for this one. You can overtake.
Okay, thanks. Yeah, welcome back to our second day of the forecasting for the extremes in the power system workshop. I can see that most of you that have been at the dinner yesterday have also made it in time. I will not make a long speech now, but I think it's maybe worthwhile going through very quickly what has happened yesterday. We had 3 keynote speeches. We heard from Vanessa and Frank about the journey of the German Weather Service coming from pure weather interest to energy meteorology interest, supporting the energy community, and the momentum, and how hard it is actually to keep that momentum, and also to how it requires dedicated people, that there will be invested in an organization that is naturally not dealing with these things. But as our task title says, the weather-driven energy system is coming to a point where weather is no longer something we can think about, it's something that we must think about and that we must integrate. So that was very nice to see that. We had then got a good overview from Martin Stensdahl on the Danish case and how the Danish system operator has been handling and is handling large amounts, and by today the largest amounts of renewables on the grid. That was very informative and always great to get a little bit an insight into the practical work also. And then we had Detlef Siebert here from SE Trade, and he came with a message that we should think about the market, whether the market is doing what it should, whether it's supporting the changes and the transition, and whether there should come changes, and how he told us that it's his fear that there will be a loss of investment coming if things do not change to the better with regards to prices. So investing into assets also always means that you have to have a business case, and if those investments do not have a return period that is feasible, organizations will no longer invest, and that will then stop our transition to the renewable energies. So I hope we can have a few more discussions today about that. And then we have had a number of really good talks, and I won't go so much into this on how to define extremes. We have been learning about weather regimes. we have also been learning about that weather regimes can maybe be, or Dunkelflaute and extremes can maybe also be defined and catched by machine learning and deep learning applications. Where we are in this is not so clear yet, but it was interesting to see that there is work ongoing, and wherever we have two different and in competition competing algorithms or methods, this is always enhancing progress. So this is good to see. And then we had a very interesting panel discussion, I think. We have learned a lot, and we have also seen that there are some applicants to become queen and king on how to steer the energy transition. And we have got good ideas from training, better education, not forgetting that part, so that we also get people that get interested in our subject. And to probabilistic forecasting, needless to say, we have been talking about that for decades, I would say almost, and it's nice to see and hear from the TSO world that they do want to have it now. So, and then the last thing, of course, data and data quality, data sharing. This is and stays the big topic, and I hope that we keep on working so that at some stage we will have the data sharing and we have the tools and the methods to share. And in the meantime, we prepare ourselves with the technology and the methods and software to handle this. And with that, I will give the floor to Irene, who is going to chair the next session.
Thank you, Corinna. Yeah, so we have our first talk this morning on extreme event risk mitigation and how this could be done by operational meteorological assessment. And I'm happy to ask Stephan to show us how this works.
Morning. I'm working as an energy meteorologist at ENGIE, and today I want to basically show you some parts of my daily work and how meteorological assessment and short-term trading can be done. I also have some examples that are quite helpful, I think. We, ENGIE, are a trading company that runs a virtual power plant, and so we aggregate a lot of wind and solar assets within Germany, and we have the responsibility to do the grid integration for all of these wind and solar plants. So we usually forecast the electricity amounts and sell these amounts in the day-ahead market. Okay, let's start with the first event. It's the 22nd of March, the most extreme event we had this year, in my opinion. This was a Saturday, so it was a weekend. It was a high wind and high solar situation at the same time. There was also some Sahara dust present over Germany. It was forecast, it was present on the usual forecast maps. And we had the problem that in the last 2 years, we had a lot of new solar installations in Germany, and in spring this year, it was not quite clear how much solar is actually connected to the grid because all the register entries are sometimes delayed and so on. And so, yeah, it could have been wrong by some gigawatts, and in spring, we often saw that solar forecasts are too low. So we had multiple critical situations here at once at this day. And so we were asking the question on the day before when we had to go to the day-ahead auction, What's the impact of the Sahara dust? Will it lead to development of some opaque clouds? Will it have impact on solar production? What will other traders think about this? What will other meteorologists think about this? And so what I did on this day was an assessment of the general forecast error I would expect on this day. Then I also checked what's the impact of the Sahara dust outbreak. Will it impact the market? What do we think? What's the impact on all the solar forecasts? Because that's usually not included there. And what's the impact of curtailments? Because negative prices were also forecast on this day. Then we had some in-house model that I built over the winter and quantified the impact of Sahara dust on solar forecasts. And the operational forecast on that day showed this map, and you see nothing. This model showed us so Sahara dust will have no impact on solar production on the next day. So what happened on this day? I show the ENGIE forecasts and observations here. So all of this is public data, what I'm showing here. So usually in all of my plots, the red line is the observation and the forecast, the day-ahead forecast is blue and the intraday forecast is violet. Here the left side, you see the solar production on this day, and on the right side, you see the wind onshore production. What we see in solar is there was a lot more solar on this day that was previously forecasted. And usually, or I think that, many traders on the day before thought about not selling all of their electricity amounts in the day ahead market, but rather wanted to keep something to have to sell it in the intraday market if Sahara dust is present. In the end, we got a lot more solar and not less solar because Sahara dust had no impact. And the result you see here on the right side, this is the wind power feed-in. Over noon, we had some negative day-ahead prices already, so the day-ahead forecast already accounted for this by curtailing some wind turbines. So more than 30 gigawatts would have been possible all day on this day. But what you see in the observation is that we had massive curtailment. 18 gigawatts of wind power were removed from the market on this day because there was extreme solar surplus. Also, because we had this very extreme balancing price of minus 3,300 euros. I classify this as an extreme event. So some people were paid absurd amounts of money to take up excess electricity on this day. We had no export capacity in the balancing market on this day, and all of these factors combined led to this being an extreme event. So now one step back, how would I define an extreme event from my trader's point of view? Usually renewable energy generation is sold in the day-ahead markets. That also means trading companies are responsible for balancing all of this generation. And for us, whenever we have a perfect day-ahead forecast, we have no risk at all. And so for us, extreme events are always related to forecast errors. Because it can lead to a lot of risk, both in the volume and on the price side. And when there's no forecast error, it's usually not a problem for us. Not every forecast error is an extreme event because sometimes prices remain cheap or remain quite stable and do not change a lot, and then it's usually no problem. So how can we manage forecast errors in general? We have production volumes that change throughout the day because usually every 15 minutes we get forecast updates that are nudged towards live data, for example, or that incorporate new model runs. Many market participants just trade these changes fully automatic without any meteorological guidelines. Some of them have traders that only do human supervision. When we have systematic errors in wind and solar power forecasts, you know a lot from this list, things like icing, fog, Sahara dust, atmospheric boundary layer regimes and their changes. This is what I show here. Typical systematic errors 1 week in summer 2022. And you see day ahead forecast versus observation of total German wind power. And you see these typical errors we see during daytime. Often the forecasts are too low. The transition periods between day and night, we get this morning and evening dips that can dive very deeply, and then suddenly 1 or 2 gigawatts are missing from the system. No forecast is able to catch this. That's solely based on NWP models. Another problem is that forecast errors often happen due to rare and unique events, and you usually cannot learn them with statistical methods or machine learning. So how can a meteorologist help to mitigate these risks? As I said, many traders just look at prices or feed-in time series like this, but they have no clue about the weather situation. Some of them look at radar or satellite pictures, but it's not done at all companies, to my knowledge. So the task of a meteorologist is usually forecasting the forecast error, communicate the confidence of the forecast, communicate and identify risks and raise awareness. So if I see for specific hours there can be a problem or forecast error, I will usually inform the traders. So another example is shown here. It's a thunderstorm situation we had this summer. Again, the day ahead forecast was way too low. The thunderstorm led to extreme gusts. We had a massive surplus in electricity production here at the 2nd of July. And after the thunderstorm passed, we had a lack of production. Here we have 4 gigawatts difference to the day ahead forecast on the next day, early morning, 3rd of July. And this forecast was from 12 o'clock, so 12 hours old, the blue line, and it was wrong by 4 gigawatts. Even the live optimized forecast could not really catch this missing energy after the thunderstorm passed. So what do you need as a meteorologist to be able to do forecasting in energy trading business? So you have to know about typical power forecasting problems. You have to know everything about energy markets, and you should have expert knowledge of synoptic meteorology, cloud physics, and boundary layer meteorology. Of course, it's hard to find a lot of people with all of these skills, so it's constant training is needed. So I've been doing this for a few years, but I'm always trying to learn new stuff, to see more events, and whenever something special happens, I also try to analyze this deeply to be able to see it next time, because next time it happens could be 2 years in the future, and most people will have forgotten it. So we are doing regular forecast assessment. We look at standard maps. For example, I showed some cloud cover maps here from the ECMWF forecasts. Then we compare models, like every operational meteorologist is doing this. For example, I show 2 cloud cover forecasts from 2 models here for the same valid time. This is the deterministic model from ECMWF and the AI model. And you see there's quite a difference in the cloud cover forecast. And this we usually, on days with partial cloud coverage, we see huge model differences also compared to models from other centers. And then it's my task to interpret this and give some insight on which models could probably be right and which models could probably be wrong. Also look at standard maps like 500 hectopascal geopotential and so on to do our weather forecast. Another example, just recently we had last weekend, 20th of September, It was not an extreme event, but nevertheless, we had some huge forecast error. We had a large low pressure area here over Scandinavia, ranging up to the UK and affecting northern Germany, bringing a lot of wind. And yeah, you see on this upward ramp, we had this oscillation here in the observation. So yeah, we had some gigawatts of forecast error, and again, the near-time forecast that was published on ENSOE was not able to really catch this. The nice thing is, when you look at weather maps, you can identify these situations. So what I show here is a potential vorticity map. All the meteorologists should know what this is. For the rest, I fear it's too complicated to explain. And so you basically saw nothing here in the wind field or in the model wind field, or also no large-scale thunderstorms and so on. But in this potential vorticity field, you see this anomaly here that was changing quite rapidly over time. So my interpretation of this is we had some low-level diabatic processes, because when this quantity changes over time, you have diabatic processes. And this is well known with these low-pressure systems that these diabatic processes can lead to gustiness, and this is what we experienced on this day, for example. So to conclude, I hope this was quite insightful for you. For us, it's important every forecast error can lead to an extreme event. Usually, if there are other aspects present, like some grid failures or power plant maintenance, cross-border capacities that are not available. So for us, it's important to have routine meteorological assessment. We think it's necessary to understand the situation, to understand the power market, and to raise awareness. And we also think that meteorological knowledge can give some competitive advantage, because we know some competitors do not use this at all, besides using power forecasts. And I think financial risks will be more extreme in the future. We have more renewable build out. We see extreme price spikes. We have bigger volumes. We have more automation everywhere. And extreme events will thus have more impact, in my opinion. Yeah, so some disclaimer at the end. All the power forecasts and observations I've shown were taken from ENSOE transparency website. And all the maps I've shown, I've taken from SMWF charts, because they provide a free license, and this is the only thing I can show here. Yeah, thanks.
Yes, thank you, Stephan. I think we have some Slidos. Maybe we make first the Slidos and then we restart the camera.
Try to restart it.
I have started.
Du musst das Receiver zur rechten Seite kommen. Das ist rechts, genau. So, ja.
Okay.
So first question is, do you think it's necessary to have a pretty all year round or even 24/7 routine meteorological support in running the energy system? Not necessary to very important. Okay, 20 participants. I think the answer is quite clear. You think we need it, but I think, yeah, when you look at all these organizations, it's not really done at the moment, both at traders, or cannot speak for grid operators, but I also don't know any operational meteorologists working there. So next question, in your organization, do you have any routine meteorological support, or do you provide the support to anyone? Only yes. Okay, thanks. Oh, that's all from me and from my Slido questions. And
I think we have time for one or two quick questions, and there is already one.
Just,
yeah.
Thank you, Stephan, for very interesting, very insightful. I think it's very important work you do. But I have a question about how you can know about the errors in your forecasts, time series forecasts. Is it by experience? What do you do when they change, when they're updated, possibly improved, maybe worse?
Yeah,
How do you adapt to that?
it's by experience. So usually these power forecasts are built from several NWP models and they change from time to time, but only one model is usually updated at a time, and in the power forecasts you do not see you do not really see rapid changes, in my opinion. And all these things like the boundary layer effects, we are seeing them since 10 years and it has never changed. The models have become a bit better, and incorporating this by all the research project because we have some higher temporal resolution at the moment, but we still see the typical errors, and whenever we have the correct synoptic situation, we see the same forecast error. So it's a lot of experience. And as I said, when you do this for years, sometimes you have events that only happen every 2, 3, 4 years, but you will recognize them because you watch out for them.
Thank you. And with regard to this topic, do you look at deterministic forecast or do you look at ensemble prediction system?
I look at everything. So I did my PhD on wind power ensemble forecasting, so all my thinking is probabilistic. But at the end, we have to trade a certain amount of megawatts. And usually all the forecasts we get are deterministic. But what I often look at is deterministic forecasts from the major centers for today and tomorrow. The ensemble prediction systems are not readily available by typical data providers, or as for example in the case of ECMWF, they are too overconfident for things like they had wind power forecasts and not really usable here. So we often look at poor man's ensembles of the major global and regional models we have in Europe, and the uncertainty you cannot imagine it for cloud forecasts, for example. It's so high even in day ahead because of these different cloud schemes they use, and this is what I mainly use.
But I mean, you can use the spread of the ensemble to forecast the forecast error, but you say it's still too overconfident. So in critical situations, the spread is not enough to build up reality in the end, or isn't it?
Yeah, with forecasting the forecast error, I meant that I try to forecast if the power forecast is too low or too high. Not if the forecast error is big at a certain point of time, but I'm only interested in the direction of the error. And for this, just an ensemble spread is not helpful.
I suggest we move to the next speaker and keep it for the networking break. I'm sorry. Thank you again. And our next speaker is Mouhamet, and he will present something on the impact of extremes on the forecasting error.
yeah.
Yours.
Hello. Thanks for offering me this opportunity to share my experience and knowledge. And as you can see, I came dressed for the occasion with wide varying shades of blue. So no surprise, I will speak about hydro. First, I would like to mention two of my colleagues that greatly contributed to this work. First, Lauriane on the left and Louis on the right. So 3 points for this 15-minute talk. First, hydropower. What is it? Some figures. My daily operational task, a little bit like Stephan, what Stephan did, what I looked at in case of extreme, how do I deal, with issue, how do I make some decision? And second point, a real world case. Basically, let's talk about an asset in an extreme condition. What do I think? What do I suggest for the traders? And the take-home message, my nice gift for you. So some key figures about hydro. As you can see here, first let's focus on the right images. It's a share of the electricity generation in Europe in 2024. And what I find interesting is, okay, for the next projection in 2030, we speak about wind, solar, but as you can see, hydro is not a pushover. It's 30% of the electricity generation. And if you compare it to what was the electricity generation coming from solar, it's higher. Okay, it's a little bit lower than wind, but it's not something that we should forget about. And as you can see in the left images, the hydro assets are really spread over Europe. And one fun fact is the biggest installed capacity is the Iron Gate hydro asset located between Romania and Serbia. So in my day-to-day task, my end goal is to know what will be the inflow available at this reservoir. So when the asset owner wants to produce, basically he will release some water from this reservoir to a powerhouse to generate electricity. And basically that's a daunting task. If you look at an hydro dam, you have two things to consider. Okay, there is this reservoir in dark blue, but in light blue is all the area where if we have precipitation, this precipitation might end up in the reservoir and influence the water level. So basically what you want to know is what would be the precipitation impact on the reservoir. So we talked about models. Stephan talked about model a few minutes ago. So are the model able to forecast accurately the precipitation and temperature over the watershed? Okay. And in case if there is model divergence, okay, it's not in case. Most of the time there is model divergence. How do you select the model that will give you the most confidence, I would say? So a nice illustration here, you have a 2-bar chart of the precipitation at one watershed. On the left side is the precipitation estimated by Météo France model AROM, really fine mesoscale model. And on the right side, it was the precipitation estimated by ECMWF IFS model. So let's focus on the 29. Okay, I think there is a layer. Yes, let's focus on the 29th. You can see there is a lot of uncertainty. The first quartile of precipitation is at 3 millimeter. The 75th percentile quartile is at 11 millimeter. We have some outlier at 23 millimeter. And here, if we focus on ECMWF, the first quartile is at 16 millimeter and the third quartile is at 26 millimeter. And surprise for this day, the precipitation that were measured were at 29.2 millimeter. So it was an outlier. So this bar chart basically they represent all the spread of precipitation forecast ranging from 5 days before the day of interest to 1 day ahead. So there is a lot of uncertainty in this precipitation forecast. So if there is uncertainty in the precipitation forecast, you will be sure having a lot of uncertainty in the inflow forecast. So we spoke about precipitation forecast. So what we do is to convert the precipitation forecast and temperature forecast into inflow forecast, meaning volume of water that will be reaching the dam. So here we have two models, one that takes ECMWF IFS input in orange, and another forecast that takes Météo France Arome forecast. So you can see that there is quite some spread. One model forecasts 10 meter cube per second inflow. The other one forecasts 8 meter per second inflow, and they are completely wrong. The realized inflow is around 5 meter cube per second. And imagine waking up at 6:30, 7, being in a lot of stress and having to recommend some forecast to the trader that might kick your butt if you're if you're wrong. So how do you deal with this type of situation? So it was Christian from Météo Suisse that talked about weather pattern yesterday. So we look about weather pattern, and here there is some geopotential map. What you try to do is to look at where the weather patterns are located. Where are the high pressure? Where are the low pressure? What is the intensity of the high or the low? Where are the intersections? For instance, here, I can guess that there will be a high wind speeds because of pressure gradients. Okay, here I have a low pressure area. There would be a high tendency of having precipitation. And most important, I look about the consistency between revision. We have forecast at 0, forecast at 6, forecast at 12, and I see how the pressure pattern differ between these different initialization. Another thing that that I looked at is ensemble forecast. It was a question that somebody asked earlier. I look at the deterministic forecast and I try to know what is the percentile that is correspond to. Okay, I have 10 millimeter forecast from my deterministic model, and I have a wide range of ensemble forecasts. Does this 10 millimeter represent 25th percentile, 15th percentile, and so on? And if the precipitation of the deterministic forecast is at the 90th percentile, I will ask myself a lot of questions. Do I believe it? What does historical data tells me? And in hydro, another thing that we look at is the freezing level. Okay, does the precipitation that we will receive will be liquid precipitation or solid precipitation, meaning snow? If you get snow, then your inflow will be impacted later than if you get liquid precipitation. This is a little bit a cookbook. You have to look at all these things. Sometimes you look at one thing, other things, but these are the key things that I process in my mind to make a recommendation. So let's talk about a real case example of what an energy meteorologist does when he works with hydro asset and how he processes the recommendation. That's what we did earlier, but what is the impact of this recommendation in the profit and loss? Here we have a nice hydro asset. The hydro asset that I consider has a watershed of ranging between 50 to 100 kilometers squared. I can't disclose the exact figure because it's an operating asset. On the day where I'm focused for the study case, the reservoir is filled at 3/4, almost close to the limit. The production strategy is then to avoid spilling. And some market assumption, basically, as Stephan said earlier, the traders make some bidding day ahead. So based on this bidding, they will get some revenue. So if the forecast is incorrect, they will need to make some assumption at every hour. And depending on the price of the intraday, meaning during the day where they are making their bidding, they can lose money. So here, how does extreme are involved? First, the first extreme is the inflow. If you look at the inflow on this day, it's close to the P95, but someone might argue, is P95 an extreme? The other thing is, and on this day, it was a day with the highest average price for the day ahead marketing. Is that all? No. Here, the other thing that might make this situation an extreme is the reservoir level. We are close to the security level for this reservoir. So here, this case represents an extreme for me because there are compounding effects. First, high inflow. Second, high reservoir level. Third, high price. Basically, how did we compute this percentile? We use 20 years of real measured data. So here's some model. I will not spend a lot of time to describe it. What we get is some forecasts of temperature. From this forecast of temperature, we compute the evapotranspiration, and we have some precipitation forecast. And we use a model that is called RGR, a French model from INRAE. And this French model takes the input of precipitation and temperature to compute an inflow. If you have further questions, we can discuss it during the time reserved for the questions. So here, on that day, this is the measured inflow. We got 3 forecasts. I did not show you the 3 forecasts, but I show you only 2 forecasts. The forecast that we recommended on that day, and the worst forecast. Let's say that I woke up in a bad mood. I was not focused. I had a lot of stress, and I could have proposed this forecast. Luckily, that day I was more or less good. This is the forecast that I recommended. Here, the difference is close to 1 meter cube per second. But is it meaningful? If we look at what 1 meter cube per second on average difference means, basically, it's close to 100,000 meter cube per second. That's a lot. Even worse if we compare it to the worst forecast. So basically, the volume difference between the realized and the worst forecast is close to 269,770 meter cube per second. If you grown as a kid like me, knowing Babar, it's the equivalent of 45,000 elephants, the weight of 45,000 elephants as a mistake. That's a lot. So based on this inflow forecast, the power trader have some strategy and they make a production plan, meaning they will say, okay, I have my plans to extract the more value I need to produce at 1 hour, 2 hour, 3 hour. Here, that's a production plan, assuming that there is no forecast error. Me, King Mohammed, I say, okay, no forecast error. All the models are perfect. Life is good. So in this situation, we do not have to buy in or sell in the intraday market. We are only involved in the day ahead market. And in this instance, I will produce in almost all hours except 3 hours. I can comment that this situation is really rare. It's like winning the same odds as winning Who Wants to Be a Millionaire one time, super low. So in the second case that I focused on, I take the forecast, the worst forecast possible, the one that I showed in red. And what would be the production plan if I took this forecast? As you can see, in red here are the missed opportunities. So I would have not produced at this time, while the ideal production plan would have recommended to produce. And on top of that, I lose the opportunity in the day ahead market, but I also lose opportunity in the intraday market. So this adjustment in the day that I focus on, instead of benefiting from the 130 euro per megawatt hour of the day ahead market, I can only gain 71 or pay 18. So that's a double penalty. And okay, let's now try to quantify what would be the value that we can capture with the forecast, meaning we have this ideal case, how close we can get from this ideal case. Yeah. And before that, I have a quick question for you. Do you have an idea of what would be the revenue percentage of the ideal case that we can capture? Do you believe that's between 20 to 40%, 40 to 60%, 60 to 80%, or none of the above? I'll let you think maybe 5 seconds about it. On the best day. So for this day, the recommended forecast was able to capture 83% of the ideal case. That's quite good. And the worst basically was around 63-65%. So it was 52.70 and the recommended forecast 79.33% of the potential revenue. And this difference basically vary on day to day. It depends on the market volatility and the intraday price. But you can see that there is a high spread and there is high consequences on the recommended forecast and the model error forecast. So to conclude, so what are the impact of the reliable forecast? The impact is huge. You have a different production plan strategy depending on if you take a forecast from model A to a forecast from model B. You optimize your production plan much better if you have more accurate forecast. You can maximize your revenue, that is the two bar that I showed you earlier, 79%, 53%, 20% difference. You minimize your exposure to volatility instead of selling in the intraday market where you might get the stick if you have a negative price. You benefit from the comfortable price of the day ahead market, and you improve your physical risk assessment. In the situation where I focused on the reservoir will fill at 3/4, imagine that you have a high inflow and all the model forecasts suggest low inflow. In the first case, you might not turbine. In the other, you are turbining at full level to avoid the water spilling. And that's all that I had for you. Thank you.
I go also from
Yeah. So my first question is, in one word, what comes to your mind when you think of forecast uncertainty in energy markets? Interesting. Yeah, unavoidable. Okay, someone pessimistic. Risk. Time to get rich as F. I agree. Okay. But my personal answer would have been unavoidable. Yeah. And second question, when it comes to hydro asset optimization, which factor do you think has the biggest impact on the profit and losses? Yeah. The clear winner for you is the inflow forecast. Okay. I would say, for me, my personal opinion, that might be wrong, but I would have the feeling that it would be shared between the operational constraints and the market volatility. Why? Imagine that you make a super huge bidding and your turbine is not able to produce. Then you will need to buy in the intraday markets, and depending on the price on that day, you might be poor as F, as the opposite. So thanks a lot for your attention.
Thank you again. There is already a quick question of Christian.
Thanks for the nice presentation. I have more of a comment and an insight from the domain knowledge in meteorology. So just you stressed the importance of the meteorological forecast, which is behind the inflow forecast. So I'm not sure if this community is aware. In the US, there is a big program for the West Coast, where, like in particular California, which often suffers from drought. They have winter precipitation, and this winter precipitation is linked to low pressure and so-called atmospheric river landfalls. So there's a few events in winter which basically make the whole reservoir filling it up, but also a threat for flooding. Yeah. And to better manage that, there is now a program since a couple of years, an operational program to improve weather forecast, the AR Recon, and basically the hurricane hunters, which usually track the tropical cyclones in summer. They fly over these sensitive regions and do a lot of additional measurements which go into the meteorological forecast. They show that this has a real impact in the precipitation forecast for California, and therefore they can better manage their hydro plants for flood protection and heating the drinking water for the coming hydrological year. So there's a real program how to improve these forecasts of hydrology for hydro management. And just check AR Recon. If you Google that, you find that it's very transparent. They have a lot of research, and a similar program is going on next winter now in Europe. Okay. So there's a German team around KIT making a field campaign together with AR Recon, doing also these targeted observations in the Atlantic. And we look if this has an impact on the precipitation forecast in Europe as well.
Thanks a lot for the insight. I wasn't aware of these experiments.
I was about to say that we have another research task to the team that Tim yesterday came up with. One quick.
Yeah, I have a question. I am wondering, okay, precipitation needs some time to be converted to inflow.
and we have a big dam. I mean, it's the best case we can have. We have a big storage. How sensitive is the variations of precipitation? I mean, the error, the forecast error of precipitation compared to the trade actually, because there is so much in between. What are the time constants? Because okay, we are not with wind power. Okay, if you make a mistake in the prediction of wind, I understand. The transfer function is real time, but here you have a big dam. I mean, if with this kind of storage you have a problem, I don't know what you need. You would need not to have a problem.
I would say I'm working with two types of dam. Dam where the reaction time is 1 day, and dams where the reaction time is 10 to 11 days. And the thing is, depending, for instance, in France, some dams were put there because there were already natural boundaries for the reservoir. And the reservoir storage is not that big. While there are some areas they really manufacture and they really thought about a huge reservoir so that the precipitation have an impact on 11 days. But here in the portfolio, you have varying range of dams, and we have to accommodate the dams where the reaction time is, you have precipitation and within the day there is reaction. It's really depending on the watershed extent, I would say. Reaction time, yeah.
So what does it mean 1 day? What does it mean 1 day? That I mean, when you have some uncertainty or some forecast error in the precipitation, you will see this error 1 day later.
Within the same day and 1 day later. It's really depending on the watershed size.
Okay, then I suggest we continue to the next speaker, saying thank you again, Mouhamet. And our next speaker, Strauss from Austro Control Digital Services.
Thank you, Irene. So, hello, everyone. I'm going to switch gears a bit with this topic. I want to talk and stimulate some discussion on with you. This is not going to be a scientific talk, and I'm certainly not the most knowledgeable AI expert in the room. But I do work at a company, Austro Control Digital Services, that caters to two sectors that are related or that contain critical infrastructure. So what we do is we tailor solutions, weather solutions, to integrate weather impact into decision-making of these critical infrastructures. So to give you an idea of what this could be about in either of the two sectors, about 2 years ago, we built a system called Simona that is an AI-based image recognition system determining visibility conditions at airports. The system is now operational at 6 airports in Austria, and air traffic controllers will decide based on the results and the condition monitoring of the system how many aircraft per hour they can allow to land at a given airport. The other example I want to bring your attention to is one that is more, it's closer to the core of this workshop, the project with the Austrian TSO, Austrian Power Grid, on extreme production anomaly detection and attribution for Austria's wind power. In Austria, we have two an interesting combination of conditions in wind power, being a very high concentration of wind power in the east of the country, and second aspect is a pushing of wind farms into the higher terrain of the Alps. So both bring a need to be very weather and extreme weather aware, and that's what we're building, or what we have built for the Austrian TSO. So both these systems involve AI or machine learning to some degree. And given the criticalness of these applications, we need to ask ourselves, how safe are these AI-driven decision support systems? So that's the theme or the starting point for this presentation. To give you some more context and to bring this even more into the topic of this workshop, I want to simplify things, simplify them a lot actually. Traditionally, people in this room on the forecaster side have produced forecasts, and they have provided them, say, as is to the users. Those users can make their decisions based on the forecast without much, or were able to make these decisions without much further information. For example, when it comes to maintenance planning. So no really high stakes decision making here. Today, or more recently, these forecasts and the decision making have been coupled more closely to optimize the application variables. For example, to make bids on the market or to make decisions on load balancing. And the next slide is sort of a claim for what's coming next, tomorrow, or maybe the day after tomorrow. Forecasts will become decisions as forecasting and decision-making systems are becoming even more integrated with each other. Artificial intelligence will have a major role in this, to a point where decisions will be prescribed or even acted out by AI-powered systems, for example, operating the system-critical power grid. Now, to give a more real-world example, not so real-world because it's very simplistic, but think of these three stages as providing a prediction. The prediction for a case are really made up, but it's a case that's semi-extreme, I would say, at least for Austria, a wind power downramp on the order of 2.5 gigawatts occurring with an oncoming storm event. Well, no, I'm sorry, with an behind a storm event, say, it's really made up, which is predicted to occur in the control area of a grid operator in a time frame of 1 or 2 or 3 hours, with that said magnitude of 2.5 gigawatts. That's a prediction we make, we pass it to the grid operators and leave for them to decide what to do with it. Going a step ahead, at the stage where we learned, or we think we learned enough of the system behavior, we can make a prescription. We can say, this coming night, starting at 22:45, request reserves on the order of 2.5 gigawatts to compensate the missing power as anticipated. So we make a recommendation. In a few years from now, we can think of systems as being much more integrated in decision-making or acting themselves. Tonight, starting at 22:45, I will request reserves from gas power plants at locations XYZ to automatically balance a power loss of up to 2.5 gigawatts. What could possibly go wrong? So that's the core of this talk. A lot could go wrong if I didn't conceive the system seriously. The database could be incomplete. So the system or the AI acting within the system could possibly not know that the power plant Y is currently in maintenance. A much more common mistake that we see already today is that the case is outside the so-called operational design domain. In other words, the ramp event of this case is not included in the training data set because it's an extreme, or because it's just rare, because I didn't expect it. The complexity, the event as a whole could be too complex for the automated system to handle it. Simultaneous cold spell, reserves exhausted, you name it. Last but not least, as we transition from human intervention in our systems to more automation, to full automation, we need to think about the interaction between the automated system, AI, and the human operator. There's a dual intervention in the system before it's fully automated might not be thought through well. So these are really the a few ideas of things we should and must care about when we head towards this our goal in the future. So we need to do our AI safety homework. Now, the energy sector is not alone with this issue. Many other sectors are, the automotive sector, the aviation sector. That's one I have a bit of an insight into, so I would like to take a peek into that sector with you. The interesting thing when it comes to AI in the aviation sector is that about 2 years ago, a big centralized effort was started by the European Aviation Safety Agency. They started providing guidance for how to use machine learning and AI in aviation. Guidance that aims at guiding applicants introducing AI and machine learning systems into safety-related or environment-related applications. That guidance is anchored in existing EU AI regulation. When it comes to us, or when it comes to forecasts, AI quality assurance is probably the most interesting subtopic in this effort. To give you some more detailed idea of what this guidance is about, it's about guiding applicants how to do proper data management, from collection to labeling to preparation to allocation, how to verify the data, how to test, validate, train data set, just to how to do machine learning properly in a guided and pre-regulatory framework. To give you some more insight, and here you can see that it gets, when you're the applicant of a system and you want to have that certified by an authority, you have to think about lots of things. Or you, this is at least how it's thought that the European Aviation Agency. To give an example, the applicant of a system to be certified should describe the machine learning model architecture. They should do an analysis on stability. They should prove the robustness of the trained model in adverse conditions. So think of adverse conditions as those conditions not occurring very often, those conditions are occurring without the full data set at hand in the live operations, and so forth. So it's really a set of prescriptions of provisions a developer of a system should take account of. Now, this is a big effort, and it's a really complicated roadmap to finish that effort, but it's a centralized effort, and that's so interesting, at least as far as I'm concerned. It includes stakeholders in dedicated meetings, 200 participants at this year's AI meeting, pilot projects. It combines a top-down regulatory approach with a bottom-up, including the stakeholders, and it will go from these guidances and guidelines to regulations in a time frame of 2 or 3 years. So this is what I can report from the aviation sector. Now, I want to ask you, do we need to care about AI safety in the energy sector? I want to ask for your opinion using my slide of questions. Explicitly put the second, which is now second there, because I want to be aware that, of course, this is not the only thing on your minds, especially when it comes to operators of infrastructure. But still, I mean, I'm kind of curious how these two rank towards each other. And that's fine. Thank you. We'll go to the next question, please. Okay. Okay. Not all are visible here, but you should see them, the full selection on your smartphones. Interesting. One. Well, that's so interesting because I was expecting, I was expecting at least the European institutions to rank much higher. They don't. Okay, thank you. Third one. There's the third. Yes. We have defined processes, defined standards, liability, regulations, test cases, search collaborations. Interesting. Thank you very much. I have a few more slides, 3 more slides. Since still typing, I'm sorry. Because I didn't want to come unprepared. So definitely there's ongoing projects in the energy sector, and I can only give you a few highlights here. Projects, testing and experimentation facilities, AI effect, Smart 4S. I forgot to put that on here, but it's definitely something to keep in mind from past few years. Efforts by the European network system operators, including their research and development roadmap. Last but not least, and I was really surprised to see that, and that's my last slide, there's currently a call for consultations until 5th of November with the European Commission on a strategic roadmap for digitalization and AI in the energy sector. Workshops have been organized, one of them last week, concerning risk of AI in the energy sector. So definitely there's going on something. And the question I want to put out there and follow up in the discussions is it something we should keep an eye on, or maybe even think about contributing? So thank you very much.
Hey, Lucas, one quick question.
Thank you, Lukas, for the very interesting talk. Every time I hear about decision making and automated decision making, machine learning, my question is, who's then the accountable person? So if the machine learning makes a decision and it screws up and something horrible happens, then who's to blame or who takes the accountability?
Yeah. So I don't have a direct answer to this question. All I can say is 2 things. And the energy sector is certainly not alone tackling the question. I mean, I named the other sectors that automotive is probably the one where we see these autonomous driving cars and the consequences of accidents. The other thing is we don't switch from human to fully automated. So there must be a phased, staged transition, and how to conceptualize that. Maybe that's the important question at the moment.
Thank you again.
Thank you very much.
And next one up is Corinna. Yes, Climate Resilience and Adaptation Initiative.
Thank you. Yeah, good morning, everyone. For those of you who haven't met yet, my name is Corinna Draxl and I'm with EPRI. Today, I'm going to talk about EPRI's Climate Resilience and Adaptation Initiative, or in short, the Climate Ready Framework. There. So what drove us back in 2022 to establish this framework? So the picture when we launched READi was that electricity as a fraction of total energy consumption in the US has been increasing, and it was projected to increase up to 2050 very rapidly, actually. And then 3 years later, when we look at the projections, we see that the energy consumption is also projected to increase, mainly due to US data center growth. So AI has its price. We need to produce energy for that. And the projections are, or the estimates are, that the consumption is expected to double by 2030 from 415 terawatt hours to 945 terawatt hours. So that is about 530 terawatt hours that we have to produce additionally. And if we think about such amounts of power, additionally to the fact that the power system of the future will be both more weather dependent and operating in a changing climate, then this becomes very challenging. Okay, so extreme weather and climate change have an impact on the energy system, and the components of the energy system that are impacted are energy demand. Think about the planet's heating, people need more air conditioning. The electric grid, for example, extreme heat can decrease transmission and distribution capacity. It has impacts on wind, solar, hydropower, and geothermal production. For example, we heard a lot about Draxl yesterday. The thermoelectric power plants could be impacted, for example, if higher air and water temperatures decrease the power plant efficiencies, or the oil, gas, and coal production can be impacted, for example, if extreme winds damage the platforms. So additionally, extreme events come with a cost. So billion-dollar disasters are growing in cost and increasing in frequency. So you see here on this top graphic, which is a very known graphic put out by NOAA, that shows that how costs increase with time. Here on the y-axis, we have cost per capita. And this graphic shows also what kind of extreme events contribute to the increased costs of extremes. There's other resources out there that calculate insured damage estimates, for example. And the point here being that without informed and timely adaptation, costs from climate disasters are likely to increase. So we asked ourselves, how can we better evaluate risk and make decisions regarding extreme weather and climatological impacts to the power systems? So a lot of our members joined our Climate Ready efforts. Here's a map of those that did. Also a list of the companies that did. We had 2 members from Europe join the effort as well. And we also established a Climate Ready affinity group. So those were experts from about 110 organizations, including academia, consulting, finance, insurance, NGOs, national labs, government, and regulatory bodies. And they all helped us address the critical challenge of resilience and adaptation in the energy sector. And so Climate Ready was born. It was a 3-year initiative that officially actually ended in April 2025. Oops. Yeah. But we're not done yet. We will continue this effort. So about the initiative though, the goal of the initiative was to establish a comprehensive, consistent and collaborative framework for climate risk assessment for the power sector. We had 3 work packages that are, you can see here. The first one about physical climate data and guidance. The second one about power system asset vulnerability assessments. And the third one about system modeling and investment prioritization. There's a QR code. You can, basically everything that came out of Climate Ready is publicly available and it's available online. We also, in terms of output, we organized more than 350 events, workshops, and speaking engagements, and we produced more than 60 deliverables and 68 media spotlights. Again, you have access to all of that if you want to. And because that's such a high number of products that people need to go through and organize and find what they need, we are developing a Climate Ready chatbot to query and summarize and make connections across all these deliverables. Okay, so now going into the weeds a little bit about the framework. So the key framework products are categorized and mapped as guidance, references, and tools. So guidance meaning, for example, they can help you execute a climate resilience assessment, for example. Those are how-to documents that explain how to do certain things. We put out references, and those are supporting resources that provide deeper understanding of the guidance and the tools. And then we have the tools themselves that can be implemented to deliver an outcome. And one of these examples is the risk tool that I showed you yesterday. I'm really glad, Irene, that you brought up story maps yesterday, or storylines, because we also developed some of those in the context of Climate Ready. So those are interactive deliverables illustrating physical climate risks to the power system. And the ones that we produced were evaluating local climate change impacts, one about projected future hurricane-related power outages, one about climate-driven variability in wind and solar cogeneration, and one about climate-informed power system modeling. And again, Texas serves here as the case study. We also put out training classes. Oops. One about physical climate data, where we explain climate data, how they are produced, different climate models, emission scenarios, and projection data. We also talk about, in this training, we also talk about trends and understanding of extreme events. We have one training about hazard exposure and vulnerability assessment, and one about climate resilient investment prioritization. And in that one, we talk about assessment scoping, impact and consequent assessment, and resilience decision-making. So now I want to go through each of the work packages and tell you what specific research we've done in those. This is very sensitive. So workstream 1 is about climate data, and workstream 1 enables more informed and confident application of climate data in the power system. Okay, so in terms of guidance documents, we published the Climate Data User Guide. That's basically a website that tells you all about climate data. Then we published also the Climate Hazard and Exposure Assessment Guidance. In terms of references, we published the Climate Data Gap Assessment that lists limitations of current hazard assessments and climate data. We have one document that talks about compound hazards. And we developed an approach to produce hourly future weather time series, because as you know, normally or usually climate projections are not an hourly resolution. But yeah, we developed an approach where you can develop these hourly snapshots. And in terms of tools, we developed the climate data inventory, which can help you identify relevant data from historical and protection data sets. And we also published the wildfire tool inventory, and that lists products, wildfire risk products for specific applications. So one research area that came out of this work package was led by my colleague Eric Smith, who worked together with Kent State University to leverage machine learning to project future tornado activity in the United States. We have several products that talk about that, also a journal paper. And basically in this project, as you know, climate models are better at projecting larger scale phenomena, atmospheric flow, precipitation, temperature, but climate models do not project changes in tornadoes and cannot reliably simulate changes in many of the key ingredients for tornadoes. And so this group leveraged machine learning to use variables that are actually available from the climate models, such as pressure, temperature, humidity, to define the tornadic environments and project changes in tornadic environments. So this is an example of using proxies and machine learning to forecast future extremes for which projections are not readily available. Okay, moving on to workstream 3. In that workstream, guidance, resources, and tools provide key information to facilitate robust assessments of asset vulnerability and response. So questions that have been answered or tackled in this workstream were: how are power system assets potentially vulnerable to various weather hazards? What is the specific relationship between a weather hazard and any unwanted outcome for each specific asset? And what factors can modify these relationships? What adaptation strategies are available to minimize unwanted outcomes? And what are the relative costs and benefits associated with each potential adaptation strategy? So again, I have a list here for you of the products that came out of workstream 2. So we have the Asset Vulnerability and Response Assessment Guidance, the Climate Vulnerability Assessment Guidance, that's particularly for the nuclear sector. And also we put out information about fragility curves for quantifying climate risk in the electric power sector. Then in terms of references, we have Asset Vulnerability Literature Review Series, and those are five volumes. And in terms of tools, we have the Power System Asset Climate Vulnerabilities and Adaptations Inventory. And that is an online inventory of vulnerabilities, adaptation strategies, and other resources. And I want to show you a screenshot of how that looks like. For example, you can go in and as a search bar on the left, you can search for your assets that you're interested in and also climate hazards. And what it spits out then is information about certain assets, what vulnerabilities that those assets could have depending on the climate hazards, and then which subsystems or components can be impacted. Okay, and that brings me to workstream 3. Workstream 3 developed a framework to prioritize climate resilience investments by integrating climate data, asset vulnerabilities, and power system performance. In terms of guidance, we have the Planning Guide for Power Systems, which provides a framework for climate-informed resilience modeling and power systems. And then we have the Investment Guide for Power Systems, which provides a model-driven approach to justify climate resilience investments. In terms of references, Texas is again our case study where we put out climate-informed power planning information. We also have one document that talks about practices for representing climate impacts in bulk electric system models, and one that is about metrics to evaluate the effectiveness of resilience strategy deployment. And last but not least, we have the risk training tool that I showed you all yesterday. And with that, I've come full circle and we'll conclude. So if you have any questions about anything that I might not be able to answer because I might not have worked on it, then please send me an email and I can route the questions to the subject matter experts. Or you can, if you're interested in Climate Ready, we have a specific email address that you can address your queries to. Thank you. have one slide out, if I find the mouse. Yes. There we go. So I was interested, what is the most important application for you or related to power systems that you would like AI to help with? Yay for humans. A lot of forecasting, interesting. Downscaling, that's interesting. Okay. Writing code, yeah. Interesting. So that's kind of help with whatever you do, basically. Yeah. Thank you.
Yeah, thank you again, Carolina. And we shift the questions to our networking break afterwards for the coffee break and move on to the last speaker of the session, Markus Schwab from Meteomatics. Thank you.
Taking some time.
Memory pool. While we wait, is there any question to Caroline? Because then we can take that, so we're not so focused about that. So it can, in peace, load. Was there any question to Caroline? Or another question?
Yeah,
all would accessible for free.
Yes.
I would maybe like to hear ask whether they are, is this all focused on the US?
Mostly, yes, for now.
The data, but the models can be.
Yeah, for example, the REST tool, I mean, for example, with the REST tool that I showed you yesterday, right, you can input your own data and put in your own specific. So a lot of it is for that.
Okay. Now it's yours.
Okay, thank you. Okay, I recognized already we are far behind the schedule.
So for now.
I really
we can
like to speak up here. I come with a more holistic view how to create a new weather resilience 2.0. So I was asked to talk around, so what kind of extreme weather events there exist, what directly will hit the assets or the infrastructure from the grid operators. Renewable power forecasts, there also exist a lot of extreme weather events, obviously, but we heard already several speeches already about this topic. I always like to start with the red monkey, because the red monkey is known as a very adaptable animal in a changing environmental condition. And that's exactly how I see the situation for grid operators at the moment, right? We see more and more weather extreme events based on climate change. Grid switch planning is becoming more frequent, and we need to avoid power outages. So what kind of severe weather events there might exist? We have seen already several answers here. Thunderstorms, I've seen it quite often already. So lightning strikes can hit overvoltage damage, or even heavy wind gusts with supercells in terms of downburst could happen. Also, this was a very famous topic in 2024 in Europe. We have seen several flooding events, heavy precipitation events, what are directly hitting local network stations or substations. We could also think the opposite. More heat waves, obviously, where the transport capacity will be limited when we rely on dynamic line rating solutions. We have seen this so-called Hitzeflaute event, another German expression. And yes, we also see already more and more wildfires in Europe. The opposite during the winter period, freezing rain, wet snow, in-cloud icing together with wind can finally end in line galloping and can heavily hit to a pole break. Just as a reminder here, so Europe is the fastest warming continent. We have seen temperature increases since the mid-90s of 0.5 degrees, roughly. But what are the impacts? When we take a closer look here, pretty obvious, two main things will happen. We will see 4 times higher heat waves, and we also see already 50% more heavy precipitation events, and even also the intensity of these events will increase. When I try to imagine what a grid operator or how a whole life cycle for a grid operator looks like in terms of increasing situational awareness for these extreme weather events, right? So they want to get the warnings as early as possible, obviously. Then they want to monitor the situation 24/7 in real time. They need to adapt grid operations. They want to validate potential damages in real time. And when I'm going even further, they want to activate emergency plannings as soon as possible or allocate the engineers in the field. They need to do troubleshooting. Yes, they also need to document downtimes. That's also obviously important, that they're aware of any critical assets or infrastructure to strengthen the assets finally. So this is somehow where I would say these kind of exercises are needed for grid operators. And I would say there exist definitely a lot of pitfalls of selecting different weather tags. It's always about precision and accuracy of forecast knowledge, pretty obviously, but there exist also further challenges. We need to deliver these kind of data in real time to the grid operators, and we also need to think of scalability and flexibility of these kind of solutions. Because in theory, we need to forecast millions of assets from DSOs or TSOs in real time. It's not only always about the forecast model itself. So how does a perfect world looks like in terms of weather resilience? In my point of view, 3 main building blocks are needed. High performance computing to detect these small-scale, rapid changing weather patterns. First exercise. Then we need to build one Stargate to the weather world to make any kind of weather data in real time available. We are thinking here of a 5-dimensional room. And when you have done this exercise, you want to build any kind of solutions on top of it. I call it a kind of MetX, a solution with endless possibilities. That's my perfect word. So what do we have to do? I also call this Starware to Heaven. We need to collect a lot of data. Global forecast models, regional forecast models, observation data, satellite data, radar data, all this whole bunch. The more interesting exercise is how to store these data in a very smart way of these kind of 5-dimensional rooms. We are talking here about petabytes of data. And then you want to build an interface on top of it that you can query any kind of data you might think of. It could be points, lines, polygons, gridded data. This is not a straightforward exercise when we want to think of reaction time of milliseconds. And when you have done this in the right way, you get the full freedom. You can query the data or the raw data. You can build any kind of front-end solution on top of it. You can build your extreme weather warnings for that, or you can even operate a hyperlocal forecast model. So, but these three main building blocks needs to come together. Yeah. So a diversifying weather tech, it's becoming more important, but yes, there exist also some challenges still. We have a gap of observation data of the lower boundary layer. We don't see so many radio sondes at the moment. We have a whole bunch of different forecast models. Traditional global forecast models, regional forecast models like the ICANN-D2 or thermal prediction systems. Then we are also having these new kids on the block of AI forecast models popping up every day nearly, right? But there's also a need, in my opinion, for a European super high resolution forecast model. Recently, the TSO Innovation Alliance was announced, and weather and grid resilience is one of their most important topics. Make it even more complicated. We can call it AI, machine learning, however you want to think about. For me, AI is just a fancy word. Let's be open and honest. You want to do some additional data tunings on top of it. Can be real-time calibration of surrounded observation data, can be any kind of nowcasting mechanisms of picture detection, or we can also think in a 90-meter downscaling based on the NASA Terra data. For this, you need a lot of working space. Data storage is not so expensive, but the working space doing these exercises in real time. And then you want to bring all these technologies together. I always called it a technological multiplier effect. Yeah, the beauty is coming when you combine high performance computing with a weather API solution built on top, a weather map visualization tool, or severe weather warnings. Here you can see a meteor drone flying up to 6 kilometers. DWD is already testing one of these drones. They can observe temperature, humidity, pressure, and wind speed in real time. And these kind of information obviously are super important for the initialization moment to cover extreme events like thunderstorms, foggy situations or icing. Yeah. And now the drone is already flying down. It's taking 60 seconds. It's going super fast, right? And when you start thinking, ingesting these kind of data in a pan-European forecast model to optimize the forecast quality, these are no satellite data or radar data in the background. These are forecast data. There exist already today forecast models running on 1 kilometer resolution with hourly updates for the next 72 hours in 50-minute temporal resolution on 80 layers. This is a massive exercise. I always like to show our data center. It's running on 100,000 CPQs, and we are consuming 275,000 kilowatt hours per month. This is expensive, right? Some examples finally for data fine-tuning. Here an example of ex-Hurricane Kirk. Left side Euro 1K, 1 kilometer, right side downscale Euro 1K. Now you see the red areas on the hills. This is coming in real time from the 90-meter downscaling. Or doing these live data calibration when some supercells appears. They have a strong value in the nowcasting mechanism. We recently also joined the E.ON Grid Up Startup Challenge. It's about real-time crisis management, mainly coming from their situation. Together with the DSO grid operator VSE, they were facing the Saarland flooding in 2024, and they were just reacting. 16 substations were just shut down because they were flooded. I'm happy to show you some further examples. In the inspirational talk, also the Saarland flooding, for me, it's all about increasing situational awareness during these situations. Thank you. Yes. I have some Slido questions, but perhaps we can skip the first two because we had already seen some similar questions.
Is it better? Was it that one?
Exactly. I guess that's an interesting one here. So where do you see the largest challenges? Technological challenges from a meteorological performance, how you can increase the situational awareness. So what kind of technologies, mechanisms, AI tools, computer capacity, data processing is needed to make these data in real time available. So there is a whole bunch of different answers somehow. Yes, it's always about data quality, in my opinion, but we, as a meteorologist or climatologist, quite often forget to think about the data storage, data processing, and making the data in real time available. So we could have the best forecast model in place. When you can query the data in real time, we don't create any value. That's my opinion on this view. Thank you.
Let's take that one also. I think the first one was a good one that I would like to. That's a very quick one.
Okay. What severe weather events will be the greatest challenge to secure grid operators' assets infrastructure during climate change? Obviously, also depending where we are. If you're thinking in Europe, North America, or even in Europe, there exist different opinions. I found it quite interesting, to be honest. I think flooding events will be a real challenge in the future. So we just heard, I just read an article this morning on the island Ibiza. They were recognized 300 liters per square meter. It's just a question where the next bomb will fall.
Okay, thank you again, Markus.
Yeah.
One quick question.
Of course.
Of course.
I was wondering if you could elaborate just briefly on the 90-meter downscaling. You said you only use terrain data, nothing else?
Roughness length data, so land use data and terrain data mainly.
Yeah, thanks for a nice overview. I agree the data availability is key, but regarding the sparse observational network and having 90-meter data, how are you evaluating it? And what is the skill, can you say?
I'm not the programmer of the 90-meter downscaling. Yes, obviously, you can evaluate the 90-meter downscaling when you compare this with observation data. When you include, besides the downscaling, on top also real-time observation data, then you can see the spread from extreme weather situations, so you can further improve, including this. I always say, let's imagine we are somewhere in the Alps. There you see the more structure in the terrain, so far outperforming the 90-meter downscaling is becoming. So the effect is getting much stronger in a very structured terrain.
Okay, thank you very much. I think we are only half an hour late. And we are used to that, so I think we just take 10-minute break, and then we have 2 short inspirational talks before we go into our discussion round. So there will be a lot of discussion time, so I think it's easy to say we'll take only 10 minutes. So we'll back in 10 minutes, so 10 past 12.
Take it back here.
always bring yourself in to this discussion, and even if the topic drifts away from what we have planned, that's also fine. So just get all the ideas, all the things that you go around with out here. And the three topics, clearly, we want to talk about defining and predicting extremes. We want to talk about mitigation and adaptation strategies and the security aspects and cybersecurity. We have not been talking so much about it. Lukas has given us a little bit an insight from the aviation, but the floor is open to whatever security aspects, resilience, whatever comes to mind. This is what we want to have discussed here. And that's it from my side. And then I will ask Markus, or should we start with Hamid, with the quick inspirational talk. And then Hamid, where you can also already come here.
Close this or not?
Yeah. Yeah, we can open it later again, but so it would be great if we could kind of start shortly past half with our, okay.
I don't know why.
So I will make it really quick and short here. I want to show you some extreme weather events, what were quite critical for the infrastructure. Quick reminder, combining all the different technologies somehow, in my opinion, is the key here. And yeah, I guess one of the famous events, flooding we were facing in Saarland. Last year, 16 substations needed to shut down, unfortunately. And these are just examples how these kind of animation could look like in real time, right? On the left side, you see an overview of Central Europe, of the precipitation situation. Here you see active polygon warnings based on river catchments. So it's a polygon query from an API perspective. Time frame could be seen here, highest levels are reached. So these kind of things can be observed in real time. Obviously, when I think I would be a grid operator, I want to receive the warnings somehow as a trigger to observe the situation. Could be email, but we could also create these kind of multiple location tables. You have defined some critical network stations, and you only want to see the local network stations where certain thresholds are reached, so that you are doing a pre-selection. And in theory, the DSO operator of VSE are operating 3,000 local network stations. You wouldn't see anything, you want to see them pre-selected. You can also visualize the situation on a grid level. Could be substation level or also the power circuits. Here you see precipitation situation over 24 hours for the mentioned day. We also go one step further, created a flash flood algorithm. It's mainly an integral function over space and time. Where you see the precipitation situation. At a certain moment, the warnings are getting active. And behind each point of interest, there is a catchment behind. When a certain threshold is reached, the warning is triggered. Thunderstorms, we also heard quite often thunderstorms can be an issue. when we see very heavy downburst situations. This is an example of the 18th of June here. On the left side, you see the situation on the asset level. In the middle, a classic precipitation weather map, including lightning data. And on the right side, you see wind gust warnings. So there was a supercell crossing from west to east over Germany. Even here has seen the strongest wind gusts. Zooming a little bit more into the situation, we have the full freedom, just to keep in mind. We are just querying the data in real time from our API. Here is the sea asset level. Somewhere there was a break of the power ports during this moment. You see the wind gust, also the wind shear, and also the wind shear time plot. And before the wind gust, we have recognized very high wind shear situations, caused very strong wind gusts, and then power ports break down. Just as an example how you could think in a kind of visualization of these situations. We heard a little bit about exceptional contingencies, wet snow, freezing rain, in-cloud icing combined with wind situations. In theory, we have the beauty to combine all the different weather parameters for any kind of weather model, including certain thresholds. So I can easily rebuild any kind of use case of a severe weather warning. Here you see the situation on the asset level. On the right side, you see wind speed situation, the precipitate type situation. The red lines are some isolines of wind speed. It was a situation, I guess it was the 9th of June. And when you assume you are getting some triggers of these warnings, you want to continuously monitor the situation, what's exactly going on, yeah, in the operational room. So can we easily visualize everything. Another example, in-cloud icing event that happens during New Year's Eve. The asset level on the left side, on the right side, you see our own in-house icing parameter, wind speed in the background. Also some isolines of wind speeds here. You also see moving here the warnings when these combined weather parameters are coming together. And you can monitor the situation later. Thank you.
Thanks, Markus. So now we can see this the gap between what is available and what is used. So thanks for that. I think this is very useful for our discussion to come. Where are we? What is available out there? What is knowledge in academia? And what is actually used? And it's great that we have all parties here in the room. So I hope we will get a really good discussion out of that. And with that, I will just ask, thanks Markus for that. Hamid, you have to help. Who is now kind of coming from with the knowledge of the WMO. I have always been thinking about we would want to have a WEMO, that would be the Energy Meteorology Organization that is organizing data, and maybe so that's why I'm really happy, Hamid, that you will inspire us into that direction, hopefully.
Thank you so much. I think after seeing a very visually attractive, nice presentation, it's time for some boring static slides. But at least it's only 3 slides. I would like to change the focus a little bit from extremes to climate variability impact just for a minute or two, and mention about this annual publication that the International Renewable Energy Agency, together with the World Meteorological Organization, publishes every year on analyzing climate variability on renewable energy resources across the globe. In this visualization, you see wind capacity factor, the anomalies in 2023 compared to the previous 30 years as the climate standards. And as you can see, basically different countries are experiencing different change in their wind capacities. In 2022, we had La Nina phenomenon, and it shifted to El Nino in about June 2023. So some of these changes is associated to ENSO climate phenomena. A few numbers, interesting numbers here. In China, we observed a 4 to 8% increase in wind capacity. Considering 400 gigawatts installed onshore capacities in China, which counts for 40% of the total global installed capacities, it translates to 65 terawatt hour over a year increase of electricity generation for 1 year due to climate variability. And it translates to 130 watt hour per person per day, something really, really considerable. The neighboring country, India, 4 to 8% decrease in wind capacity factor the same year. And considering 40 gigawatt installation, it translates to something about 7 terawatt hour over the year. So, and it was the same case more or less in terms of increase in Southern America. And in Chile, for example, there was a specific month, November, that the range went up to 80% increase for wind capacity factor. I'm mentioning that because in each year, basically, the last section of the report dedicates to a specific topic. The first edition in 2023 was about climate change. The previous two editions and the upcoming one soon is about seasonal to sub-seasonal forecasting and the impact on the energy sector. And I know probably there are participants online from international organizations, so extreme events could be considered as the new topic for the next edition. In continuation, what we discussed yesterday during the panel, and here is a little bit my chaotic thought late last night on how I can map weather and climate services based on the language of the energy sector. And this is the idea that I came up with that probably clarifies a little bit on different type of services regarding to extreme events based on the life cycle of the energy systems. If we put the site assessment, design, installment, construction all in one group, then the type of the extremes we deal with is only one-time calculation of the extremes. So we don't deal with day-to-day, basically extremes with those type of applications, site assessment and design. I'm not sure about the wind industry, but in nuclear, there is a safety review every 10 years. So they reevaluate all the design parameters. Maybe it's the same case here. In any case, it's one-time calculation of the extremes based on historical climate data, and something that I think we didn't discuss yesterday a lot is about climate projection models. And the more we move forward, the more they become reliable, and it's important to start looking at them and extract the extreme variables from climate projection rather than using statistical models on calculating extreme based on previous data or previous historical data, which is not representative anymore for future evolving extremes in a climate change. The list of the guidelines, I just would like to mention about these two tools here. At the end, Climate Information Platform and the ClimPact software. In ClimPact, you can calculate extreme event indices based on temperature and precipitation. So there are lots of indices for different sector, energy included. And in climate information platform, you can choose any location, let's say a power plant, and you can see all the climate projection data over the next decades. It uses CMIP data as well as Cordex data. And on the right side, we deal with the operation. And the type of the services is obviously early warning system. It's day-to-day forecastings that we need. Another missing topic, I think, yesterday for further talk today is impact-based forecasting, when we take into account vulnerability and exposure of the energy facilities. And this is something WMO has started to work on. You see a lot of other types of guidelines here. But when it comes to practice, we are still at the beginning phases. And my last slide, it's just a demonstration. Sorry, the one before the last, the demonstration on different platforms I explained. Also, the World Weather and Climate Extreme Archive that I explained yesterday is basically providing extremes from 2007 all around the world. And here is the last slide. So all of those publications you saw, it's general. It's not tailored to the energy sector. But this is the first step that we took last year. And I technically coordinated this publication in collaboration with Chinese Meteorological Administration to put together a short document on early warning for the energy systems. So basically, they are quite advanced in developing these models for different types of hazards. And here is just a demonstration of what you can find in the document, and it will be available soon over the next few months. And basically, the next step will be under the Anonymous project that we bring into the application, and we will start to define a demonstration project based on the technical publication. That's the last slide. Thank you.
Okay, thank you. Thanks a lot, Hamid. So then the floor is open for discussion, and I would like you to choose one of the topics. We will have Gregor moderating the first one. That's the defining and predicting extremes. We will have Caroline and Irene at the back with mitigation and adaptation strategies, and Helmut and I are in the yellow room. We will be discussing security aspects and cybersecurity. I will, after 10 minutes, kind of use our bell. So to remind you that if you want to discuss at another place, it's time to kind of change. So our plan is to be back at it's 20 to 10:20, around quarter. Yes, it's difficult now to get the timing right. So we take 3 times 10 minutes. So you have 10 minutes to 15 minutes. We'll see how fast and how much you're engaged in the discussions. And we'll then back in around 40 minutes here to wrap up and get a little bit a flavor of what has been discussed. So please, and you may want to grab a coffee or a glass of water, and then just please go ahead. Yeah. Okay, just to have a nice background. Okay, can you please also conclude, and so we are not too much delayed for lunch. I think everybody is looking forward to that. But since we are going to end the workshop, with the lunch break, I still hope that most of you will stay for the afternoon. We have four very interesting talks in the afternoon, and besides a little bit of administrative talk and planning for the next phase, I think it's worthwhile to stay. But before we conclude the workshop, I think we had really interesting discussions. There was most of the people stayed with Gregor at the first part, and maybe this is also something that interests us most, how to define, how to actually get the grip. So I will give the word to Helmut and Irene afterwards, but we'll start with Gregor, just telling a little bit to all of those that haven't been at your group. So
thanks.
Gregor.
It's been a really nice discussion, and we got a lot of results out of it. And it's a bit difficult to structure what I tried anyway. So one of the things is that different extremes or different things are extreme for different groups, and that kind of thing we need to take care of. Are RANs extremes, or are they that just the new normal? Partly some RANs are probably extremes, but how to define that? And that goes into the definition of extremes. But also a good question was how to evaluate the extremes, and do we need databases of extreme cases that we then can afterwards look at and maybe run in more detail? There was also a question on AI and predictability. What is actually predictable? How far can we predict ahead? Can the AI be better? And how much trust do we put into the AI or any sort of automated tool versus should we still keep a human in the loop? There's also been a question of how do we deal with the increasing intensity of these extremes? The climate change is seemingly increasing the intensity, and so we don't have that in our training data. Is that a problem for the AI models? Do we actually have the possibility to evaluate these new AI models in terms of things that happen outside their previous knowledge envelope? And then some gaps were identified: fogs and clouds, seasonal scale, aerosols or Saharan dust, convections and thunderstorms. And thunderstorms also lead to less loss of solar. And maybe in the end, since these extremes are so different for the different groups, you might need some guidelines from the end users, also in terms of guiding where to put the effort, because we can't predict everything.
Yeah, so I was in a group with Mitigation and Adaptation Strategies. From pre-event preparation and resilience, during event management and response, and long-term planning and investment. And we also have a lot of bullet points on our 2.5 slides. One thing for pre-event preparation, resilience, and during event management response could be also investing more and having more backup systems like batteries available in case of an event happening. So investing also more into those systems, or hydrogen power plants, something like that. And also maybe using more smart management of the power grids, using more smart meters where we have those, and switching on off. That's an idea. A dishwasher in house, if they are programmed to do that. Then we have different types of adaptations are needed across the different sectors in the energy sector, from the power grid management, from power infrastructure, where some infrastructures are or let's say, a bit more older than I am in some regions, and they also need adaptation measures, how to deal with more heat in the future, and across the chain. We have the uncertainty in the projections
as well as the suitability of the climate projections themselves, and how to know how we can use them, and not simply using them to make the right choices for mitigations. We had a chatbot idea for making the information we have, the tons of information, more easily accessible, more easily digestible for the users and understandable, and maybe also providing some sort of guidelines on what to consider when using these data sets. And we have also the regulatory bodies. Sometimes regulations on what to do when would be ideal for, let's say, flooding events, when to lower the water in hydropower dams early enough, if we have warnings early enough for events. And also the communication of warnings. How do we communicate and not over-communicate events? And I think, yeah, we have also the tipping points, when to expect tipping points, but also development of what if scenarios. What if we have a different type of power plant there? What if we have a different type of distance between the power grid lines, especially for more heat events in the future, to ensure that we have a stable power. And there are other points on the list I'm not going to mention now because I had no time to summarize them nicely.
I had offered to Helmut to do it, but one of the most important notes should not fall on the ground. And now I'm okay. Now we have been talking about security and we have been talking about data, of course. In a way, this one has been maybe placed by me, also put in as an idea, just coming up as an idea. How can we actually close the gap between having data available, sharing data in a secure, fair, and transparent way? And like the WMO is sharing data among the med centers, there are regulations, and this is also a body of regulations, but it's working. We have, for example, the NSOE that is sharing data across the power sector on the TSO level. Every TSO collects a lot of data and knows practically everything, has all the data available, but that data is not available to all the processes inside the organization. So the idea is, can we generate, let's call it a hub that connects, and we call it the buyers and the sellers, those that produce the data or have the data available, and those that need the data, and those that provide services with the data, and those that need the services from that hub. If we think about an ideal world, then that would really encourage fair competition. It would enhance end users to integrate things because they are readily available. And we just need to have it fair and transparent. And there has to be some kind of business model, I guess. But it's actually only the very big bubble, because what we then realize that communication without the internet is something that the system operators need. There needs to be also plugins for secure data exchange that is not through the internet or mobile system or whatever. So the complexity, the further we come down, is getting more and more. And that is also one of the things that we have been talking about, that sometimes we miss a hands-on mentality, or do rather than talk. What I said yesterday, that we need always first movers. We need some that push the boundaries. And that's why it's so great to really bring this together, because we had also sharing versus protection. Some data may also have to be protected and should not go anywhere. And then policymakers, they look in a totally different way into data sharing and data availability. And then it's that one here that is going a little bit away with the, we work a lot with black boxes. We work a lot with software that we don't know how it's programmed. We don't know whether there is some other information sent out if we do something in the internet. But we need the black boxes to get an idea, and but then we also have to understand the complexity below. So what has to come first? The complexity, the complex discussion of the problems, or the overall idea and solution. So that's what also can be in such a hub, because it enables to create some kind of ideas and bring it in and see whether there is there are buyers, there are interested parties that want to try this. And no matter where it is, we heard it today from Caroline about the READi development, that you think, wow, they have developed the whole thing, but it's then mostly with the data tested and used where it has been developed. And that's why having the idea of developing things on a global basis where we all have access to it. We have the automation versus human intervention was also one of our discussions. We have heard about algo trading, and we have and we know that system operators can run fully automatic, whether data is generated fully automatic. But at some places we need a human intervention. And if we don't have the expertise, the experience, the gut feeling anymore, because everything is just automated, and there are very few people that have the knowledge of how it works, this is also a danger. So open source, evil or grace. Open source has changed and disrupted the way we are thinking and working today. But there are also some security issues that are often forgotten, and then things can also go very wrong. So security of data exchange, and then can we trust the AI algorithms, is something that that brings us back to trust, and transparency is always something that should not be commercial, that should be somehow regulated, or it should be an authority that has only one interest, and this is a fair and transparent way of dealing with all its members. So I think that's about what we have been, oh yeah, this one is also a very important one. Collaboration and diversity are challenging. If we have a diverse group, it can be very challenging, but it's also something that brings up the best ideas, I think. We can see this here. We are coming from very different backgrounds, and each background alone wouldn't come up with these ideas and wouldn't push the boundaries, because what we experience and know from one area, we cannot translate directly, but we can get an idea. We can push that boundary where we have a need. And that's why I think, and with that, I will also like to close kind of our workshop and give the floor the next 10 minutes free to any questions, comments about the last 1.5 days. I think we have really had great discussions. We had great and very inspiring and interesting presentations. So I'm going home with a head full of ideas, and I'm looking forward to bring this together and bring it to the next level in our next phase, which is going to start next year. And so please, if you have any questions, comments, I'll hand it over to you now. Or questions that have not been answered.
One question about the presentation yesterday. It was on the convective modeling, and I was basically, I forgot the name's presenter, but he found out that with his modeling, the aspect ratio of the convective cell was quite accurately described by the model. So I was wondering, how did he get to that result? Because it's highly influenced by the PBL schema that you use, the microphysics, the cumulus schema. Did he use an ensemble approach? So I was wondering, what are the details on how did he find this result?
Was this Abhinav or Max? No? Oh, that was Gerard Kilroy.
Yeah, Gerard, yeah. It was Gerard.
He's not here. I don't know whether one of the DLR people can answer. No. So we have to bring it further to Gerard. But a good question. Or is there any other comment? I mean, Stephan, you have also brought up something that I find very interesting with the potential vorticity. Something that we have also, we have first understood when we were working in the Rocky Mountains, or at the lee of the Rocky Mountains, where I tried to make it once plots of what actually IPV means in a horizontal way when these wind gusts come out of the blue. So that's also one of these things where probably some would wonder, why is this suddenly popping up?
I don't know why. I completely missed the event. In forecasting, and then I was looking at all the maps available. Could I have seen something? So I was trying to learn this. And then I saw it. What's there? Well, there was some information.
Yeah, I have a question, and maybe a bit provocative question. Is there anyone aware of such a workshop on the streets that is organized by the end user or by the users?
We have some end users here, so
would be good. Probably.
Might be a good idea. Yes.
Yeah, it's an excellent idea. That's a good guests.
So you would like to be invited, I can see. Yes, but I think it probably doesn't matter whether we are invited or we invite. But I think what we have learned is that there is a lot to be discussed. There are a lot of gaps still, as there always have been. But only when we try to close those gaps, we can get to the next levels. And Vanessa.
This brings me exactly to my question about the future. He said, okay, we have the fourth workshop within this phase.
Yeah.
What are the next steps and how do we shape the next phase? How do you or the task members plan to include these types of interdisciplinary workshops? So what are your plans? Probably, yeah, filling more gaps even probably.
Yeah, we actually have a description for the next phase already.
In the afternoon.
Phase has been approved by the IEA TCP Expo earlier this year. So we are good to go for the years 2026 to 2029. And we have 4 workshop topics already described. One is AI weather prediction, one is forecast error evaluation, one was and 2 more that I have on my slides for this afternoon. So there's some information of really available.
Oh, yeah, let's come to Helmut.
Yeah, I want to advertise that for the Germans, for the next phase, we want to participate, but also to get funding by the PTJ, Projektträger Jülich. We need letters of support. So all the German or companies also in Germany, I would be happy if you would write a letter of support for this task to send to me, and then I will send it to the PTJ that we get funding from the Wirtschaftsministerium, which is not a lot, it's just to support the operating agent, so it's not a real big project, but I sent out a letter already a while ago for the present members, but I'm always happy if there are more people or more institutions to join.
Thanks, Helmut. That's I have it here. Yeah, and I also want to make tell something. This is where you find us. We have not these fancy communication tools. We have an operating agent that takes on any email and a person that wants to join our newsletter. It's not something that is spamming your inbox. We really only announce things that we think that are important, that we want to share, if there are workshops, if there is our task meetings. So just write to Gregor. You find him also together with here. So there is all the information how to get in touch. And then I want to also tell you that we have a lot of our workshops here in our social media, YouTube. And a last thing that I wanted to say that we have had this, or we still have it running, the probabilistic forecast decision-making experiment or game, and it's still online. So if anybody wants to, after this, look into some kind of real world example on how to trade or balance wind plant with probabilistic forecast, it's still there. It's closed for the analysis. The paper is about to be submitted probably next week. And we are very happy to take feedback from those that played, and that's why it's here, because it's a bit it's a bit just very simplified web page to start it, but you can find it there. And I want to encourage anybody who doesn't know it yet to play around with it, because then we can also plan another one. And it has been developed together with the Max Planck Institute for Human Development, so with a psychologist that has been looking into things. And as I said, the analysis of that when we had it running will come soon. And with that, I think we managed.
Yeah, but before you get the lunch now, we also have a dinner this evening prepared, and I need again confirmation who will participate, because I have to call them again. Yes, so just raise your hand and then we count 1, 2, 3, 4, 5, 6, 7, 8, 12, so it doesn't. Because originally it were 24, so it's important that I call.
Registered 25, and we had yesterday registered 50 for the dinner, and we started being only 25, and they were a little bit dodgy, saying that they had reserved a room, and then there was only half the people coming. So,
but now, yeah, we will have lunch in the yellow room, where we see it there.
There's one final thing to do for us, and that's to thank our hosts from the Deutscher Wetterdienst that provided this venue and provided the lunch and so on. And especially Helmut and Vanessa Grigor for the and the others for the organization of this workshop. Thanks a lot. And then not the least, Corinna and Caroline for doing and putting together that program that I think has actually shown us quite a good overview of the extreme events over the last 1.5 days. And thank you very much. And with that, see you afterwards. Now is lunch.
Absolutely.